Fair enough. Now, last class, what did we really do? Last class, what did we really do? We talked about geostationary orbits, and I gave you a bit of a pointer into what gravitational field strength is. And essentially, what gravitational field strength is it is a measure of how much force is being applied on any object whenever the object comes into the vicinity of any other mass, but per unit mass or 1 kg of object. What is the force on 1 kg of object whenever the object is in any gravitational field? So if I have a massive object over here, and this is the mass of which we are going to discuss the gravitational field strength of. So if this is a mass and it has this gravitational field strength, right? So this is the gravitational field strength. These are the field lines. And I bring in an object M1. Now, what I want to understand is for any object, any piece of object, any piece of mass, if I bring it near the object, what is the force on this object at this position, this position, this position, and this position till infinity? But I want to understand that amount of force with respect to 1 kg of mass. 1 kg of mass. So per unit of mass of any object brought in to the vicinity of this large mass, what is the force on it? That is a field strength. That is called the field strength. Force on 1 kg of object. Okay, so how do we find out the field strength? How do we find out the field strength? The way we find out the gravitational field strength is we use the same formula, but we divide by mass. Let's see. So gravitational field strength is essentially at any random point near a mass, we define it as the force per unit of mass. Okay, so for M2, what is the force per unit mass whenever an object is brought near it at, let's say, 2 meters away or 100 meters away? For this object at 2 meters away or 100 meters away, what is the force this will observe or this will face? This 1 kg of object. Let me write that down. 1 kg. So this 1 kg of object, how much force will this 1 kg of object face due to being 2 meters away from M2 or 100 meters away from M2? Now, this gravitational field strength, mind you, will be different for different objects. M2 will have a stronger gravitational field strength. Sorry, M2 will have a weaker gravitational field strength compared to the much heavier M1. So if I bring it the same 2 meters away from M1, its field strength is stronger, right? So 1 kg, what 1 kg really does is it standardizes the comparison. So I say, if I have a 1 kg of mass and I bring it 2 meters near M1, I feel a greater tuck. I feel a greater force. And that tells me M1 must have a stronger field. So that analysis of how strong fields are is done by gravitational field strength, by understanding the gravitational field strength, right? So it is simply a measure of how strong or weak gravitational fields are at any given point. That is 2 meters away, 3 meters away, 4 meters away, 5 meters away. Doesn't really matter. Okay? Gravitational field strength changes with distance. Same with force. The difference between force and gravitational field strength is gravitational field strength is measured with respect to 1 kg of mass. Okay? Now, how do we derive it? You know force is equals to m times g. So the gravitational field strength or gravitational acceleration is given by g, which is force by mass. So your gravity, g 9.81, is the gravitational field strength. The thing that you call acceleration The thing that you call acceleration is essentially the gravitational field strength. That is what the gravitational field strength is. So if you move way away from the center of Earth, what happens to the gravity? Decreases. So that tells you that the strength of the gravitational field has decreased. So this acceleration, my friend, G 9.81 is the gravitational field strength. And 9.81 is the gravitational field strength near Earth. So near the Earth's surface. So if I am having a conversation with you about inside the Earth's atmosphere, so let's say till this distance near Earth's surface. Over here, G is 9.81 and constant. But the moment I start having a conversation about away from Earth, so like this damn far away, over here, obviously the G is different. G has decreased, or the gravitational field strength has decreased, changed. Why? Because it's really far away. Near the Earth's surface, we approximate, we assume, we estimate that it must be nearby 9.81 everywhere. If we are talking about being under the clouds, till 50 floors, 20 floors, 30 floors, G must be pretty much the same. Very little difference in height as compared to the radius. Like obviously the buildings are not even 1% of how big the radius of Earth is, right? Which is why we assume near to Earth's surface, G is 9.81 and constant. So essentially, this is what's happening over here. The gravitational field strength is given by the total force on, let's say, a 3 kg object divided by the mass itself, which is 3 kg. So if I know the force on 3 kg of object, which is, let's say, 2 meters away, I can easily find out what is the gravitational field strength 2 meters away from Earth. How do we do that? So if the force on 3 kg object is 30 Newton, I say, okay, the gravitational field strength at this point must be 30 divided by 3, 10 meters per second square. This is the gravitational field strength at 2 meters away from Earth's surface. How did we find that out? We said, okay, I have a 3 kg object. I have a 3 kg object 2 meters away from Earth's surface, and I know that the force it is experiencing is 30 newtons. So, simply on a 1 kg object over there, it must simply be 30 divided by 3. So 10 newtons of force must be applied on just a 1 kg object. So that is my gravitational field strength, 10 meter per second square, right? Okay. Similarly, I can now show it with respect to the main formula. This is, right, this is with respect to the F is equals to mg formula. That is to show you what what I mean by dividing by m. What I mean by force per unit mass. Gravitational field strength is force per unit mass. So gravitational field strength is force per unit mass. But don't we know a better formula for force? Don't we know a more elaborate formula of force from law of gravitation? Yes, we do. So can we input that over here? So if my gravitational field strength G is force per unit of mass, right? Then what is the formula of force we have figured out? G m1 m2 divided by r squared divided by m2. Can I cancel off the m's? M2? Yes. So basically what we're saying is on 1 kg of object, whenever you're canceling out the masses over here, you are making it independent of how heavy the object is. It doesn't matter anymore. It doesn't matter anymore because the masses are being cancelled, right? So now you have gm1 by r squared. This is now your gravitational field strength formula. All we did is divide by mass. And this is your gravitational field strength formula. Okay? So it's just force per unit of mass. And this is how the formula looks. Just m2 being omitted. or being cancelled out. Okay, so that is the gravitational field strength. Now, why is it, mathematically speaking, we assume gravitational field strength to be 9.81 near the Earth's surface? Let's look at the maths. So if you are convinced by the fact that G and gravitational field strength G is given by Gm by r squared, which I showed you the maths of, simple mass cancellation, nothing else. If you're convinced by this formula, well, I'm telling you, let's find out the gravitational field strength h meters above Earth's surface. What is the gravitational field strength h meters away from Earth's surface? Let's find that out, okay? Now, to find that out, what can we say the separation is? Gm divided by, what is the separation? The separation is radius plus h. Radius plus h, right? R plus h whole square. This is my separation. Now, this is where the approximation comes in. Since we have a case where my h is really small as compared to my radius, I can approximate that r, the radius, is pretty much equal to radius plus h. This is an approximation. Same r, sorry, same r. This is an approximation. I'll change the r's. Capital R. So this is an approximation, my friend. Is it accurate? Obviously not. But this approximation works. Because remember, as with point mass approximation we discussed last class, since the deviation is so small as compared to the distances we're talking about, it does not matter. The height, this small height we're talking about, let's say 2 meters away, doesn't matter. Let me give you another example. We were talking about throwing a ball around. Can we throw a ball around that it orbits around Earth? Notice what happens when I add, okay, I'm 2 meters above the Earth's surface, right? I'm 2 meters above the Earth's surface, and the radius of Earth is this massive amount, 6,371 into 10 to the power 3. Does this 2 meter really do anything to my calculation? Notice that. No, it doesn't. So that 2 meters is of no substance to the calculation. It doesn't matter. Which is why we make this approximation that near the Earth's surface, at small height, my gravity remains constant. And I can also show that to you by simply saying that when you look down on Earth, doesn't the Earth look flat? Can you make out the Earth's curvature with naked eye while standing on Earth? No, you can't. The roads seem very flat. It is pretty flat. Hence, near the Earth's surface, when you're standing on Earth, the field lines are pretty much parallel. What this tells you is the field strength is also equal everywhere. Equidistant, equidistant, equidistant. The field lines are equidistant. So the strength in here, 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 here is equal. Is equal. Because the field lines are equally distributed. Right? Near the Earth's surface, field lines are parallel. Because near the Earth's surface, the roads seem to be straight. But you zoom out, and let's say you're looking away from space. Now, yes, at this distance, my friend, the field lines, I can make out the curvature. I can make out the separation. I can make out the radial field lines. This is what radial. So now, from a far distance in space, I can notice Earth's curvature, and hence I can also see the difference in field strength. Notice the field lines are further away up there as compared to compared to over here. So the field strength, as you go along over here in this path to space, decreases. The field strength decreases. So this is another way to explain to you guys that the field strength does indeed change. It decreases, right? Fair enough. So hence, when I'm talking about small h above Earth's surface, my g, my gravitational field strength, same. Okay? Are we convinced with that? Hopefully we are. Hence, we made this approximation that radius is pretty much equal to radius plus h. The same thing. H is very small, anyways, so it must be equal to r, which is the radius of Earth. Right? After we make that approximation, we are left with the same formula, which is gm by r square. And notice it is 9.81 as expected. If you put in the values, it's 9.81. So as long as h, the h we are talking about over here is very small as compared to my radius, this approximation is valid. This approximation is valid. Now, if I'm talking about, let's say, a planet over here, right? M2. Now, this is the radius r, and this is the separation. Too bad. So, so this is the radius r, right? And now this is the extra part minus the r. So the total separation is r plus h. Here, h is very big, way bigger than the radius itself. Can you make this approximation of g as 9.81? Hell no. You definitely can't. Because h is way bigger. Here, the gravitational field strength will be wildly different. Your acceleration at this position of m2 is very different due to this field strength. Very different, very different. So the field strength of this yellow planet at this position where M2 is going to be very different. Why? Because the separation is really large. So that's how it works. That's how the distance matters. Okay, so we understand the approximation, and you will be working with the approximation in the sense that you will assume the gravitational field strength is 9.81 in multiple cases. Now, have we also explained why the G is constant near Earth's surface? Yes, I told you guys that the field lines are parallel near Earth's surface. As in, they seem to be parallel, not that they actually are. If you look at this curvature image, then you understand better that there is still a curvature of Earth, but very small near the Earth's surface that we notice. Hence, the field lines seem to be parallel. Hence, our field strength near the Earth's surface is also seems to be equal, seems to be same everywhere. But as you tread away from Earth's surface, changes. Now that is the thing. Now I want to show you guys how the gravitational field strength varies with distance away from a planet. So if this is my planet and this is my center, this is my R, and let's say this is a random distance away from this planet or Earth, right? Let's say it goes till infinity. So I have marked a diagram over here where the conversation starts from center of Earth till going to infinity. How does the G or the field strength change as you go from the center of Earth till infinity? How does the field strength change? How does the force per unit mass of an object, so this I'm marking as an object, as it is near the Earth's center, right? If I position it right at the center of Earth, what is the force on this? If I place it on the surface, what is the force on it? 1 unit of mass, by the way, 1 kg of mass. And what is the force on it at infinity? Okay, let's figure that out using the same old maths. I'm simply going to be using maths. And I mean maths as in the formula. What do we know the formula for gravitational field strength to be gm by r square. Isn't that right? This is the formula of gravitational field strength. Now, notice, my friend, that does the gravitational constant change? It's a bloody constant. It won't change, right? And the mass of Earth, no, it's not changing. I'm not changing the mass of Earth. Nothing is happening to the mass of Earth. So this is a constant. And what can we say about constant? I don't need it when talking about proportionalities. Hence, I can say G is proportional to 1 by r square. Separation I'm changing. That is, the position of this object I'm changing. I'm putting it inside Earth, I'm putting it on Earth, I'm putting it 2 meters away from the surface, I'm putting it at infinity. I'm changing the distance. And I want to analyze how does the gravitational field strength change as I change that distance. So let's find that out. Now, near the Earth's surface, what will the gravitational field strength be? What do we think? What do we think? If G is proportional to 1 by r square, right? 1 by r square. Let's say near the Earth's surface or on Earth, the separation is the separation from the center of Earth. Let's give it a value. Let's say it's 10 kilometers. Arbitrarily put, no worries. So let's say that, let's include the GM over here, no problem. G is equals to GM by 10 square. Okay, so I'm saying this is 10 kilometers. Agreed? Note that down and let's do a bunch of calculation. 10 kilometers. If that is the case, then I can say G at surface is going to be GM by 100. Agreed? Great. Great. Now, what happens if I do this? I put it 1 meter, or rather, let's say, yeah, 1 meter away from the Earth's surface. So over here, 1 meters. This is 1 meter. Okay. Plus the radius. Plus the radius. Yeah. Plus the radius. And what happens in that case? What happens is G is GM by 1 plus the radius of Earth, which is 10 kilometers, if you remember. So if that's 10 kilometers, so I have to turn that into, okay, over here, let me convert this into meters, guys. Since SI unit is meters, let's have all the conversation in terms of meters, no kilometers. So, okay, this answer is correct. 1 by 100 into GM. Okay, I've just converted into meters. Now, in this new case, when I have it 1 meter away from the surface, let's say now the total distance is from the center of Earth 10 meters plus 1 meter whole square. Okay, so 10 plus 1. 1 meter away from Earth's surface and 10 meter one is the radius. Fair enough. So what is my G now? 1 by, so 11 square is 121. So this is now the new gravitational field strength. Can we all agree on that? Can we all agree on that? I just did the calculation. Okay. So this is the gravitational field strength when you move away from the Earth's surface. And this is the gravitational field strength when you're on the Earth's surface. What has changed? The gravitational field strength decreased. Decreased. And if I give you an even better example where you see how the square law really applies, let's say that R over here is 1 meter and R over here is, let me make your life easier and say 2 meters. And let's say another position, 3 meters. Let's see how it varies in this case. So I have G is equals to, G is proportional to 1 by R square. let's now use the proportionality, right? Let's now use the proportionality. So G is proportional to the first one, let's say 1 by 1 square, which is over here on the Earth's surface. So this is 1. And now let's increase R by 1 meter, convert it to 2 meters, right? So G is now 1 by 2 square. So G is 1/4. Now let's increase to 3, right? What happens? G is now proportional to 1 by 9. What's happening over here? We can see the inverse square law acting. As we increase the radius, my gravitational field strength keeps decreasing from 1 to 1/4 to 1/9. Are we getting that? The gravitational field strength keeps decreasing as you increase the separation. Hence, my friend, this is the inverse square law. Increase the separation and you have your field strength or the force per unit mass decrease. And that is the interesting part, and that is what you see in the graph. What do we have in the graph? We have the gravitational field strength, meter per second square, being plotted against separation from the center of Earth. What is this point? What is the origin over here, my friend? This is center of Earth or the planet, right? So from center of Earth, from the surface of Earth, I'll tell you what happens between the center and the surface. That's a bit more complicated derivation, and it's not in your syllabus. So this yellow line is not in your syllabus. What is in your syllabus is from the surface of Earth till infinity over here. So if I extend this line till infinity, this curve till infinity, this is how the force per unit mass near the Earth's surface till infinity changes. So where is the maximum force felt on any object? On the Earth's surface. So you can bet your money that if I have an object, 1 kg of mass or 100 kg of mass on the Earth's surface, it experiences the most or highest amount of force. If I push it away till infinity, the force on the object keeps decreasing at an inverse square rate with respect to the separation. And we saw the calculations over here. And this calculation will be very important to you. This proportionality that I used is very important to you. You saw how if the radius goes twice, the gravitational force gets divided 4 times. I increased the radius twice from 1 meter to 2 meter, and my gravitational field strength went quarters, right? It went quarters. And if I increase it to 3 times, then it goes 1/9 of the initial force. Whatever force was over here, it goes 1/9 that if I put it 3 meters away. Sorry, this is 3 meters away. Okay, so this is what's happening. This is how the proportionality works. If force is F over here on the surface, force will become 1/4 of F at 2 meters away. And if force is F on the surface, force will become 1/9 3 meters away. 1/9 of F. This is how proportionality works, and it's very, very important for you lot. Okay. You have to understand what's happening over here. Very important. Do we understand what has happened from the surface till infinity? As they move an object from the surface of Earth till infinity, are we all clear on this? Give me a thumbs up. Yeah. Good. Now what I want to show you guys is what happens from the center of Earth, till the surface. So inside the Earth. This is interesting. And this is rather not new syllabus, so I will still teach this. I feel like it's important to know how to manipulate equations. So now this part where we're talking about inside the Earth, what happens? Well, qualitatively speaking, before I get into maths, with the maths I can instantly prove it to you guys. But qualitatively speaking, if you allow me to erase this, if you don't have a problem with screenshot or anything, I've erased it. Let's see what happens inside the Earth. If this is my Earth, right? This is the center of Earth, right? And let's do this. Let's position a piece of object mass, 1 kg of object. Let's keep it simple. Over here. You know what happens over here? Now, since you're inside the object, something has happened. This object stops feeling a force, stops feeling a force in this entire shell of Earth, from this entire marked shell of Earth. Why? Why did that happen? Why? Because it went inside Earth. And what happens when you're inside Earth is all the mass. So if I draw a line over here, what better color do I have? So notice one thing. All the mass in this part has a very strong pull on this object. Very strong pull. Now, similarly, this massive part of the object, right, shell of the shell, we're calling this the shell of Earth, right, has a very weak pull on the object, but it is also far away. And that is why it has a weak pull. But the amount of mass over here that we're discussing is a lot. So this amount of object has a very weak pull on the object on over here on the shell. Now, same thing happens for this part as well. This part and this part, the pull for those two parts is equal, similarly distance away from the white object. So what is happening over here? The force that this shell of Earth has on the object gets cancelled out by the force of this shell that it has on the object. So essentially, my friend, what's happening is, again, whatever this portion of the mass of Earth's shell has on Earth over here gets cancelled by the force of this shell on the object. So all the forces get cancelled out in the shell. So if I have gone inside by 2 meters, if I went inside Earth by 2 meters or 2000 meters, you know what happened? All the mass in the radius of that 2000 meters has no effect on me anymore because it gets cancelled out, equally cancelled out by each other. It gets equally cancelled out by each other. Now, the same doesn't happen for the mass inside. You will ask me, doesn't that happen for the mass that is inside as well? No, how does it? If my object is over here and there's a massive mass over here, all of it pulls inward. If I divide the object into multiple pieces, multiple cubes, all of these cubes are pulling my white object inside. So the white object still feels a force towards the center of Earth. It still does. It's just that, you know what happened? The shell of Earth over here, however much of Earth I dug into, that shell of Earth stops having an effect on me. So that force, net force, has decreased on me. I still feel a force. I still feel gravitational force, but that is for the mass that is inside of Earth now, or whatever amount I have in front of me. that I have yet not dug into, that this mass yet did not dig into. Okay, so essentially, if I put this, right, if I get this object to move and it goes way in right now, then what happens? Now the mass, this entire mass in this ring, in this shell, stops having an effect on the white object because the forces are being cancelled out. Hence, my friend, hence, my friend, as you go inside Earth, the force decreases. So as you move away from Earth, from the surface here till infinity, force also decreases. And as you go inside Earth, force also decreases in both direction. As if you tread, force will keep decreasing. That is the conclusion. But as you move away from Earth till infinity, the force decreases as inverse square law. And how does it decrease inside Earth? Any idea? It decreases inside Earth linearly. Linearly. This straight line is a linear demonstration. It is a linear decrease. And that is what I will prove you with maths. Does it really decrease linearly? Let's find out. Now, deriving, just over here, just follow the steps. You may think I didn't figure it. I don't think I figured this out. Partly, yeah, but like I also looked up on the internet to find out because I was very confused. It wasn't in our syllabus, so I was just very confused as to what happens inside Earth. So I just went up and looked into, I guess, Stack Exchange or something, and I found out this odd derivation, which I'm showing to you guys. So just follow this for now, okay? This is the proof of that gravitational field strength, the acceleration keeps decreasing as you tread inside Earth, right? So the proof says, notice now, can I explain the density of Earth, or can I denote the density of Earth as mass by volume? Yeah, we can, right? So I have Earth over here, and the density of Earth can be given by mass by volume. Let's assume that Earth is uniformly mass distributed. So it's a perfect sphere and uniform mass distribution. If that is assumed, then this um, derivation is accurate. Okay. Now, density, mass by volume. If I take the volume and density on one side, this is the volume and this is the density and this is the mass. So can I say while density, again, this is why the approximation that Earth is a perfect sphere and uniformly distributed is valid or important because I am considering my rho, that is density, to be constant throughout Earth. This is where very important that your rho should be constant. So for this, we are assuming the density of Earth throughout Earth is constant. Otherwise, this derivation is not valid. In essence, in reality, it is also not valid because the decrease is very ununiform. It will be, I don't know what it is like, the true shape, it will be a bit different. It will not be a perfect line. Okay, it just will be a bit wobbly or something like that. I don't know. It's just different. Okay. So, but we can assume it since for this entire chapter, we are assuming Earth to be a perfect sphere. We can also assume over here. Now, if we assume that, what happens is we can say, okay, my density is constant throughout Earth. So I can say my volume is proportional to mass, or the other way around. My mass is proportional to volume. Can I say that from this? What did you learn about proportionalities? If I just omit the constant, I can find the proportionality between two variables, which is mass and volume over here. Okay, this is one of the equation. Let's call it equation 2, that mass is proportional to volume. The other one is, can I express the volume of Earth as 4 by 3 pi r cube? You guys know this from spherical geometry. And from this, while this is all a constant, my radius is a variable. So I can say V volume is proportional to the cube of R. Can I say that? Yes, of course I can. Two proportionalities. What is the common variable? V. Can I join this proportionality now? Can I say, can I say my mass is proportional to V and V is now proportional to R cube? Yes, I can say that. I can say that. That's the beauty of proportionalities. We can relate multiple things together. From this, I can also assume, okay, if mass is proportional to volume and volume is proportional to R cube, well, my friend, mass must also be proportional to R cube. This is my third expression. I just joined the two proportionalities out. Okay, great. Now, do we also know the formula of gravitational field strength? Yes, we do. G is gm by r squared. Now here, what I want to do is I'm gonna say this is r. This should also be r. Okay. So now, if this is the formula of gravitational field strength, from my knowledge, can I use the proportionality over here as well? Yes, I can. So can I say that G is proportional to mass by, sorry, it's r square by the way, r square, because I'm omitting which which variable am I omitting over here? Sorry, which constant am I omitting over here? The gravitational constant. Okay, so G I'm omitting as I introduce the proportionality sign. And what I find is the gravitational field strength is proportional to mass and inversely proportional to the square of separation. Now, if I have that, can I join the previous equation over here into here somehow? Can I do that? Yes, we can. How do we do that? I will simply, I will simply say, okay, taking this, G is proportional to mass by r square. But my mass is also proportional to the cube of r. So this mass is proportional to the cube of r. So I will just omit this m and say r cube. So I just omitted the m and said r cube. Now, if you cancel off the powers, you're left with G is proportional to R. What does this tell you? This now tells you as you decrease the radius inside of Earth, all of this analysis, by the way, inside of Earth while the density is constant. So if I go inside of Earth over here, my gravitational field strength G must decrease linearly. What is the proportion over here? Power 1, power 1. So it's a linear proportion, my friend. So inside my Earth, if my decreases from here, my gravitational field strength should 100% decrease linearly. This is the proof. Okay, this uh, this is the proof. Okay, you can take a look at it. There's a very interesting video over here. Um, how does how would you fall if you had to fall down through a tunnel inside of Earth? So this one. So if you just search up how long it takes to fall through Earth, then you'll find this video, and you can watch this very interesting video, and you get that insight of gravitational fields over here as well. So you see how relatable what you're studying is. Okay, interesting video. You can look into it. It's not in your syllabus. I'm just putting it out there. All of that is good and dandy. This, if I have time, I'll include. You can just take a screenshot for now. This is a question. And if you just read out my explanation, you'll understand a heck a lot of it. But I will now first finish the content before going into this. Taking a screenshot. Great. Now, this is the topic I want to cover. Gravitational potential energy, then you have gravitational potential, and lastly, you will have astrodynamics. These three things, if you're done with pretty much everything, okay, of gravitational fields. Now, gravitational potential energy, you guys already have learned it at some point, but what you have learned is completely wrong. That is what I want to tell you guys. You guys have learned about gravitational potential energy being mgh. And if I have a surface over here and a box over here and I lift this box by 2 meters, what is the gravitation? And I'm telling you, this is 1 kg. What is the gravitational potential energy of this object? You will do the calculation and say 1 times 9.81 times of 2, and this should give you some, I don't know, 19.6 or something. I don't know. I'm just doing it off the top of my head. So this is probably, am I audible? Am I lagging? Or can you hear properly? If I'm lacking, do let me know. Okay? Uh, okay. So over here, what I'm doing is I just multiplied mgh, and I'm telling you guys, well, you would answer me. The gravitational potential energy of this box is 19.6 joules, but that is wrong. This is the change in gravitational potential energy. This is what? Change in gravitational potential energy. So by going from point A to point B, this is indeed the gain of gravitational potential energy, but 19.6 joule is not the gravitational potential energy of this object. No, it is the change or the gain of potential energy that the object went through as I pushed it against gravitational fields. So there are gravitational fields, attractive fields between the object and the earth. What I did was the object wants to fall down, but well, I picked it up and pushed it through the gravitational fields, pushed it through the sky, and I transferred my mechanical energy into the object by providing potential energy. How much? 19.62 or something. Okay. So I transferred my energy into it. Right? Right? So this is the gain. This is the gain of energy. But this is not the innate energy of the object in this position. No. You can't just say that the GPE of the object is 19.6. No, that is wrong. And you will learn why that is wrong. You can say my box gained 19.6 joules of energy as I lifted it up. You can say it's a gain, but you can't say that that is the energy of the object. Why? Let's see. What is the true definition of gravitational potential energy that you guys need to know? It is the energy that an object possesses due to its position in the gravitational field. Notice this definition. Gravitational potential energy means what is the energy of any object, let's say A, at any given position in a gravitational field, for example, that of Earth. Okay? So the gravitational potential energy is only, and only determined by position. So if A is in this position over here, different gravitational potential energy. And if it is over here, different gravitational potential energy. Less or more, we will discuss. Less or more, we will discuss. Don't get confused by gravitational force over here. The force increases as you go towards the Earth's surface. Sure. Gravitational potential energy is not force. Gravitational potential energy is not force. Okay. It is the energy that an object possesses due to its position in any gravitational field. And we will look into the maths of it and the proper definition of it as well. But before that, I want to explain something to you guys. And that is the sign of gravitational potential energy. We always say, okay, I pushed it up from the surface of Earth to 2 meters away from the Earth's surface. I put in energy and I say the GPE of that object is now 19.62. No, this can't be positive. The GPE of an object can't be positive. That is wrong. That is the positive change. So my change is positive 19.62. Yes, very good. But this is not the GPE of the object. That is the change in GPE of the object. So what is the GPE of the object? Let's look at some demonstration over here so that I can clarify the sign issue even before I get into the formulas. This is where most people get confused. The sign. If I have an object A over here, right, and I push this object and I take it to infinity, what happens? If I take it to infinity, this same object at infinity, does it feel any force at infinity? Away from Earth. So basically, at infinity, the gravitational field of Earth, fields of Earth does not exist. Field of Earth at infinity doesn't exist. That's why it's infinity. So at infinity distance away from Earth, which is really far away, I mean, there's nothing called infinity, but basically saying really far away from Earth at the theoretical infinity, does Earth have any field line over there? No. So does the object A feel any force due to Earth? Does object A feel any force due to Earth? No. No field, no force. Okay? So object A is free at infinity. But does that mean object A at infinity has any energy? Answer is no. So at infinity, my object, I'm telling you guys, has zero energy because it is free from all forces in the universe. It has no tug, no push, no pull. It is just there. It exists stationary or roaming around, doesn't really matter. It's just there. Okay. I mean, technically, it shouldn't roam around for it to have zero energy, but we're talking about potential energy, gravitational potential energy. So, for potential energy to be there, there should be some amount of pull from somewhere. But at infinity, what did we discuss? Is there any pull? Is there any field? No. Is there any force? No. Hence, does it have any potential energy at infinity? Does A have any potential energy at infinity? No. Are we clear on that? So at infinity, there's no way object A can have any potential, any gravitational potential energy. Okay. Now, if I bring this object close to A, I mean, the middle ground, what happens? You will say, okay, the object must have increased gravitational potential energy. And you must say, okay, if it comes closer to Earth, the gravitational potential energy must increase even more, even more. But that is wrong, technically. Why you want to know? Because look, when I am pushing this object A from this middle ground to infinity, what did I tell you guys? I'm pushing it. There are field lines, my friend, there are field lines towards the Earth. And I am working against that field line and I'm transferring my mechanical energy to A and then pushing it away to infinity. So I am transferring my energy to A. I'm transferring my energy to A. I am doing the work. But you guys also know that at infinity, gravitational potential energy is zero. So what the hell happened over here? I increased my energy and A has zero potential energy at infinity. The answer over here is by maths. With respect to maths, A has a negative gravitational potential energy whenever it is in the vicinity of another object or in any gravitational field. Since since the gravitational potential energy of A in any gravitational field is negative, all right, now I can increase the gravitational potential energy of A as I push it to infinity to zero. This is how the gravitational potential energy at infinity is what? Zero. Because we're starting from negative gravitational potential energy. So from negative, I'm transferring my energy into A and increasing its gravitational potential energy to zero at infinity. Are we getting the point over here? So I'm transferring my energy into A and increasing its gravitational potential energy to zero. Okay? And when we get closer, when A gets closer, it keeps getting pulled in by Earth. So it loses all the energy I transferred to it. This A loses all the energy as it gets attracted by Earth. All the work that I did to push it away at to infinity is lost. And you know what the gravitational potential energy of A is as it travels towards Earth? It's negative. It's negative. Negative work is done. That is the answer. That is why gravitational potential energy of any object is actually negative. Is actually what? Negative. Are we clear on that? Any question, do let me know. This is where most people are confused. They can't understand why GPE is negative. Rightfully so, because it challenges an idea that you guys have had from a young age. That is the MGH formula. And since that idea gets challenged, it's hard to understand why GPE is negative. But that's fine. That's completely fine. So, in essence, bringing an object from Earth to A, I'm doing positive work. So, positive work is done on A. But the GPU of the object is still negative. I'm just increasing. So, if it is minus 1000 joules at near the Earth's surface, at A would be minus 500 joules. And at infinity, it would be 0 joules. So, if I put out the numbers right there, you can see what's happening. So I'm increasing the gravitational potential energy of the object. I'm again increasing as I move it away, but it is always negative. Now from infinity to A, what happens? If it's 0 over here, then it's minus 500 at A. Okay? And again, one more thing. I can take the object A from this position in infinity to A, or I can take it from this position to A. It will always be minus 500 at A. Gravitational potential energy only depends on the position. So it doesn't matter what journey this object did, from it came from this scribble and whatever nonsense it did. If it comes back to this position, its gravitational potential energy will be minus 500, irrespective of whatever journey it took. Irrespective of whatever journey it took. So for this distance, there will be a specific gravitational potential energy. For this distance, there will be specific gravitational potential energy. So regardless of whatever journey this object did, whenever it is in this same position, same gravitational potential energy. Okay. And as I go from infinity to A, I've lost energy minus work has been done. Negative work has been done. Why? It goes from 0 to minus 500. Please carefully understand that. Okay? So, what is GPE outside Earth? The real definition. It is the work done in bringing a mass from infinity to the discussed point. So, if I am talking about this point, which is 1 into 10 to the power 6 meters away from Earth, what is the GPE in this position? In this position, the GPE defined at 1 into 10 to the power 6 meters away from Earth, it is defined as the work done on the object A as it was brought from infinity to this defined point. That is 1 into 10 to the power 6 meters away from Earth. So, what is the GPE? The work done in bringing the object from infinity to this point. Okay. And what is that work done? Minus 500. Because energy was lost. That is the GPE, my friend. That is the GPE. That is how we defined. So the energy lost in bringing the object from infinity to a defined point. It can be this, any point, doesn't matter. Okay? So that is how we define GPE. What is the formula of GPE? The formula of GPE is minus, careful, minus GMM by R. What's the difference between this and the force formula? GMM by R square. So what's the difference? A, there's a negative sign. B, it is just R, not R square. In force, it is R square. In gravitational potential energy, it's just R. Now, normally, most teacher will probably leave it at this, which is fine, and you will be asked to remember this, which is also fine. I have no problem with that. But if you want, if you want or not, I will still be showing you the derivation of this formula. So this formula is actually derived. Okay, how do we derive this formula? I'll show you the derivation. Okay, so you may think, where does this energy formula come from? Yeah, from good sources, and this is a proper derivation. But what is the unit of GPE? Joules. And nothing has changed. Energy is energy. It's always joule. Okay, and it's a scalar quantity. If you guys are confused. So gravitational potential energy, you will often see it denoted as this weird U. It can be symbolized as that, and that's fine. So they can say U at 500 meters away from Earth is, let's say, minus 1 into 10 to the power 6 joules. And that's fine. That is how they write down gravitational potential energy. Anyways, so don't get confused between force and gravitational potential energy formula. And by the way, this formula comes from the force formula. Okay. 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 Don't get confused. Don't get confused between the two formulas because most people will use them interchangeably, and that's a problem. Now, how do we find the formula? The GMM by R, negative GMM by R. How do we find it? Do we remember this formula? Sorry, this graph. Inside the Earth, it is a straight line. Okay. And from the surface till infinity, the gravitational field strength or gravitational force decreases as inverse square. So this is how the graph looks like. Okay, this is how the graph looks like. Now, how do we find the work done from infinity to a defined point? Let's say R. Integration. Have you guys heard of the formula? Work done is force into distance. Do we know this formula? Yes, you do. What happens if you guys have done pure math? What happens when you integrate from infinity to R? A defined point. Let's say if I draw, right? This is the center of Earth, and well, the surface needs to be a bit bigger. Okay, 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 great. So look, this is the center, right? This is the radius of Earth, right? Why did I draw it like that? Wait, let me reposition this. I misplaced it. It seems about right. Okay, now. Okay, sorry. Okay, now it's perfect. So look, this at the center, you have zero force. At the center, the force gravitational field strength is zero, right at the center of Earth. And at the surface, it is maximum. Okay, the force is maximum. So from surface to the center of Earth, it's a linear decrease of force. Phenomenal. Now, from the surface of Earth till infinity, what happens? Force decreases as inverse square law. And how do we find the work done? From infinity to r, let's say this random place near the Earth's surface, near the Earth's surface, from infinity to this point, you integrate. You integrate from infinity to r. What are we integrating? We're integrating this curve, this area under the curve. And what is this area under the curve? If this was a, if this was a, why isn't it undoing? Okay. If this was just a rectangle over here, the area under the line would have been r minus infinity, sorry, infinity minus r times whatever the force is. So distance times force, force times distance. And that gives you what? Work done. Literally over here, all you're doing is integrating from infinity to a defined point r, which is over here, and you're integrating the work done. See, you integrate from infinity to r, and you find the work done because it's simply force times distance. That is all the integration is. That is what the area really defines. The area under the curve is simply fg times the distance. Is that not it? Yes, it is. So that's how we find the formula. And let me show you the formula derivation. This, do you need it? No, but can they just throw a curveball at you and ask you to integrate? Yeah. Uh, Initially, I remember I used to not remember the formula when I first sat for my exams. That is, I used to remember no formula. I still don't till this date. So one of the formula will be given on the marks formula sheet, and I would take that formula and start deriving other formulas. So half the paper for me would be derivation of formulas because I could remember none of the formulas. So I would derive the formula. Half the paper is just that, and then use this GMM by R formula for my question because I hated remembering formulas. So in essence, knowing the derivation is very important, and I will show you uh, why it's so important, especially in thermodynamics when doing ideal gases. Because I did that the most in ideal gases. It has a bunch of equation. I couldn't remember any of it for the love of God. Right? This still is easy because one is just r squared, the other is r. That one has a ton of formulas. Okay. So knowing how to derive, always good. And you guys are studying physics. In essence, that is all you guys do in physics. Manipulation of equation. So now over here, if you just know a bit of calculus, what do? You integrate Fg, this is how you write it. You integrate the force from infinity to r. Big why? This positioning is very important. Why am I putting r on top and infinity at the bottom? Right? Why am I doing that? This is the final position. Because what is the definition of GPE, guys? What is the work done from infinity to a defined point? So my initial point is infinity and my final point is what? R, the defined point or the point I'm bringing the object to. Is that clear? Great. So now what do? We integrate. So GMM by R square is my force Fg. dr is the element, distance element. This is how integration takes place. Okay, I'm not going to explain the calculus over here. Hopefully you guys remember from pure maths. Now, GMM is a constant. Can I take it out of the integral? Yes, my friend, I can. And I took the GMM out of the integral. And what I'm left with is the integration of 1 by r square. What is the integration of 1 by r square? Can I just write it as this? Yes. How do we integrate this? This will become, if I integrate it, r minus 2 plus 1 divided by minus 2 plus 1. And essentially you have minus 1 by r. That is the integration. Now put in the limits, that is r and infinity. So now you're going to get, notice the sign. This is the sign of GPE. And now finally, you have minus 1 by capital R minus 1 by infinity. Okay. Now minus 1 by R plus 0. 1 by infinity is 0. Okay. So now your gravitational potential energy is simply, right? So this part inside the bracket is what? Minus 1 by r. So when you multiply again, what do you get? What do you get? That the gravitational potential energy is minus gmm by r. There you go. I have derived the formula for you lot. Okay? This is how the derivation looks like. This is why gravitational potential energy is negative, mathematically speaking. I am not giving you the qualitative answer over here. I did the qualitative shenanigan over here. I told you guys pushing, pulling, attraction. I told you guys why it's negative. But by maths, with respect to maths, why is it negative? You saw the maths. When you integrate it, you get the negative sign. When you integrate, you get the negative sign. And that's why gravitational potential energy is negative. So literally all the explanation I can give to you for it being negative, I've provided to you. Okay. This is why it's negative. Okay. Fair? This is the formula of gravitational potential energy. Now, the other formula. This formula, you will now ask me, I mean, you're not, but I'm still saying it. MGH, where does this come from? This is also a valid equation. This is not an invalid equation. When they ask you why GP is negative, because negative work is done in bringing an object from infinity to a defined point. So you can say about that is one thing you can say. Second thing you can say, attractive forces cause the energy, the potential energy to be negative. Whenever you have attractive forces, the energy is negative. That's the second point. Third point, you can just show the maths. You can simply show, that's one way, that's a long way to show it, a long way to write the answer, but that is also a valid answer. That when you integrate it from infinity to a defined point, my expression is negative. So that is the proof that taking a point from infinity to near a mass, GP is negative. Okay, so there's a bunch of things you can say, right? So you can say there's an attractive force between two objects. Whenever you have attractive forces, the potential energy is negative. That's one. Two, you can say, as I have an object, this is a longer explanation. The longer explanation is, if I take an object from near the Earth and push it to infinity, the energy of the object increases to zero. Okay, and as the object travels from infinity to near Earth, that energy decreases to a negative value. Okay, so you can also say that. There's a bunch of things you can say. You can talk about attractive forces causing the potential energy to be negative. B, you can say, you can do the derivation of the maths and say, okay, I have a negative sign over here, whatever I did over here. This, and that's the mathematical proof that gravitational potential energy is negative. C, you can say, whenever I have an object and I push it to infinity, I'm transferring my energy to it and it increases to zero. Since the object's energy increases to zero, that means near the Earth, the object's energy must be negative. So that is a third thing you can say. So there's a bunch of things you can talk about depending on how many marks you're being assigned. Okay, hopefully I've answered the question. And of course, you can look at the marking for how much of a concise answer they want. I used to write in everything I could think of. Okay, I didn't care if it would like if I had to write way more than the assigned marks. So if I remember, it would be probably 3 or 4 marks. So I would just write according to that. Hmm. I would write way more than needed, and then there's no point of cutting marks. That's what I did. Okay. Any confusion about that? Any confusion about the gravitational potential energy being negative? I also there's I actually have more over here. So like extra explanation. Okay. So I also have extra explanation for the potential energy being negative. Here, there you go. You can take a screenshot. There's a bunch of things that a bunch of people said. I just noted it down. Okay. Okay. Coming back, and that's not as necessary. If you just follow the 3 things I said, fair enough. That's a valid answer. Now, what was I saying? Okay, I was just talking about the MGH, right? Now, this is a valid formula. This is not an invalid formula. This is not a formula that they just made up. It's a very valid formula, but it is an assumption. What is the assumption? The assumption is we're talking about gravitational potential energy near the Earth. That is, again, let's say the height is the height of a building or the mountains, and that's it. We are not talking about height being beyond the Earth's surface till, let's say, Mars or something. Okay, that's a really big distance. There, the gravitational potential energy is different. No question about that. But for small distances above Earth's surface, this formula works. Why? Because look, for all the values of height, you're considering G to be 9.81. Okay, which is why this formula is only valid for small distances above Earth. Now, this, as mentioned to you guys, this is del GPE, change in gravitational potential energy. So there are two caveats to this equation. One, this is not the gravitational potential energy. This defines a change in gravitational potential energy. Second is for this to work, we are talking about near the Earth's surface. Those are the two caveats with this equation. Okay, if you understand that, let me tell you that this equation does indeed come from this equation, and that has another derivation, which I will show to you guys. So this MGH comes from this formula. Okay, how 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 does that happen? Let's see. If an object is raised from the Earth's surface, let's say by h meters, del h meters, right? Now we want to find out what is the change in gravitational potential energy using the original formula. Okay, using the original formula, that is gm by r. Okay, negative gm by r. This is what we want to use. GMM, sorry. Okay. Now I want to find out the change in gravitational potential energy over here. So I take, let's say, over here, what is the gravitational potential energy? And what is the gravitational potential energy over here? What do you think is going to happen? As I push it up, the gravitational potential energy becomes less negative or increases towards zero. Increases towards zero, right? So that is what's going to happen. So if that is what's happening, essentially, then well, let's find it out using the formula. Let's see what my expression stands like when I do the derivation. That is UF, the gravitational potential energy, final position, minus gravitational potential energy, initial position. So let's write it down. Final position is going to be minus GMM by R plus H, right? That is this position. So R plus H is my separation from, if this is the Earth's center, right? If this is the Earth's center, this is the R, and this is the h, right? So r plus h. Okay, hopefully clear on that. And then minus the initial gravitational potential energy, which is again minus gmm by r. Okay, right? So now you open the brackets and you see that essentially what I have is minus gmm by r plus h plus gmm by r, right? So now, can I just take the constants outside the bracket? Let's just make our life a bit simple. And as I take the GMM outside the bracket, I'm left with minus r plus h plus 1 by r. Fair enough. Can I do a bit of LCM over here? Yes, we can. So I'll have minus r plus h divided by r plus h times r. This minus r and r gets cancelled, so you're left with h by r plus h times r. And now over here again, we do another approximation. What is the approximation? Can I say r plus h is approximately equal to r? Yep, we can. Why? Because this h is so small compared to the radius of Earth that it doesn't really matter. I can assume this to be r itself. So if we do that, we get that gmm by h by r square. This is what we get. Because if this is r, then this is also r. So r times r square. Now, what does this look like? Gm by r square. What does this look like, my friend? Isn't gravitational field strength gm by r square? Do you guys remember that? So now all you have is gmh. This is g, this is m, and this is h, or mgh. And this h is simply the del h, or the change in height above the Earth's surface, right? This is how the formula is derived. And I hope you understand the derivation really well over here. Okay? Okay? So this is the derivation. This is how we use approximation and find out the change in gravitational potential energy. It's a very neat trick. It's a very neat derivation. Looks good and makes sense as well. Hopefully, you guys understand this derivation bit. Now, the next part, or not the last part, but gravitational potential. What is gravitational potential? Similar to gravitational field strength, gravitational potential says it is the work done per unit mass in bringing a mass m from infinity to a defined point. So we are basically, all we're doing is bringing a mass from infinity to a defined point, and we're measuring the amount of energy. But this mass must be 1 kg. That is all it needs to do. That is all it needs to be. So gravitational potential, similar to gravitational field strength, it is simply the amount of energy required to bring 1 kg of object, 1 kg of object from infinity to any defined point. That is all it is going to be. Okay. So gravitational potential, this is how gravitational potential will be written, and you will see this, so don't get confused by it. And this is simply going to be u, or gravitational potential energy itself, divided by the mass. So what you're essentially finding is gravitational potential energy on 1 kg of mass, because you're dividing the mass away. Same thing we did in case of gravitational field strength. Same thing. So if I write down the formula for gravitational potential energy, that is simply minus gmm by r divided by the small mass, and the mass and mass gets cancelled off, and you're left with minus gm by r, right? So this is the formula for gravitational potential. So on, let's say if this is my massive Right. So if this is my massive Earth, what is the energy it takes for me to bring an object from infinity to this point? And this object must be worth 1 kg. So for 1 kg of object, how much energy it takes to bring from infinity to this point? That is gravitational potential. Okay, that is gravitational potential. The moment it is more than 1 kg, so let's say I'm talking about 5 kg, I will multiply gravitational potential with 5 kg and I get the total energy for a 5 kg object. That is pretty much it. And your gravitational potential will be written as joule per kg. Okay, joule per kg. How much energy needed per kg of mass? That is what gravitational potential is. Now, why is gravitational potential negative? This is the graph, by the way. So if I have an object that is, let's say, the center, let's say, not the center, this is the surface of Earth or the center of Earth, doesn't really matter because in your syllabus, how gravitational potential energy changes inside Earth is not included. So since that is not included, I won't even get into that because the derivation is way more complicated. Not way more, but quite a bit more complicated. And the graph will look a bit different in that case. But hence, I'm not going to overcomplicate your life by talking about gravitational potential energy inside Earth. So forget that. You guys don't need to know what the gravitational potential energy is inside the Earth. So just consider this to be, near the Earth's surface. We're talking about near the Earth's surface, right? And what's happening is as my gravitational potential energy increases, right? As the gravitational potential energy increases, we are treading towards, sorry, as the gravitational potential energy increases, we are treading towards infinity. Okay, so we are being pushed away. We're being pushed away. So if this is a massive object and I want to transfer my energy into this object, I have to push this object away to infinity. Okay, so then the object will gain energy by increasing its gravitational potential energy to zero. Okay, so this is how the graph looks like of gravitational potential. So we are increasing the gravitational potential as we move to infinity. Okay, this is how the graph looks like. Again, this may come in your exam where you're asked to draw the gravitational potential. So near the Earth's surface, right? Near the Earth, it sort of, this is an asymptote. Okay, this is a bit of an asymptote. Why do we have this asymptote, guys? Gravitational potential is given by minus gm by r. Where am I writing? Gravitational potential is given by minus gm by r. So if I just cancel the constants, omit the constant, you have minus potential energy is proportional to minus 1 by r. So on your Desmos calculator or somewhere, if you just plot 1 by r, you will see the graph given is like this. You can try it out on your home. No worries. And what you will see, the graph looks like this 1 by r, right? So this is the same thing. Because of the 1 by r, you have an asymptote over here near zero. Okay. This is why the asymptote exists. Okay. So as you move towards the Earth, what happens? It increases toward in the negative direction. So it becomes more negative. So your gravitational potential energy becomes way more negative as you move towards the Earth's surface or get inside Earth as well. So inside the Earth, gravitational potential energy will also decrease. It will keep decreasing. Okay, is that clear? But inside the Earth, no conversation should happen on the question paper for gravitational potential energy inside the Earth, as far as I know. But yeah, so this is the bit I have covered. Now, how do you find out uh, the change in GPE for two masses? So I have two masses over here. And what is the gravitational difference in gravitational potential energy between the two objects? Now we know that the gravitational potential energy, change in gravitational potential energy can be given by mgh, isn't it? But over here, this wouldn't work because the separation is really large, my friend. The separation is really large. Is what? Really large. They're really far away as compared to their radius. So here you can't make that assumption that g is constant, right? Hence, over here, you have to do something different. What do you do? What do? We use the same original formula, that is gmm by r. And we say that for mass m2, if it's going from r1 to r2, so these are the kind of maths that will come on your paper. This is what you guys need to know. This is the math that will come in your paper. So if my mass m2 goes from position r1 to position r2, what is the change in GPE? What is the change in gravitational potential energy? So I would say the change in gravitational potential energy is simply whatever the initial potential energy was, that is, let's say, at R2. So it's probably going from, where is it going from? It's probably going from position 2 to position 1, let's say. So it's from here to here. So I will say whatever my final position is, sorry, it's going from position 1 to position 2. My bad. So whatever my final position is minus GM M by R2, this is my final position, minus whatever my initial position is. What is my initial position? My initial position is minus GM M by R1. Is this clear? So final position minus initial position. This is all I'm doing. So what is the gravitational potential energy in the final position R2 minus gravitational potential energy initial position 1? You simplify this, and what you get is this formula Gm times 1 by R1 minus 1 by R2. This is for gravitational potential and this is for gravitational potential energy. What is the difference? Here there's an M, here there's no M. So small mass is omitted in gravitational potential. Why? Because we're talking about 1 kg of mass. 1 kg of mass. So gravitational potential does not have small mass m included. But gravitational potential energy, yes, it is included. Okay. So essentially, this is how the formula will look like for change in gravitational potential energy. Gmm 1 by r1 minus 1 by r2. Okay. It is always better to write this out. This you will get confused. You know why? Why do I say this? You will be confused. What is my R1? You will be confused. What is my R1? You'll be like, oh, wait. Is a longer distance R1 or is a shorter distance R1? And you will have the minute or 5 minutes you will spend first understanding what is my R1 and R2. Better you write the entire formula. What is my final position? Put it over here. What is my initial position? Put it over there. The reason I say that GPE, change in GPE can be positive or negative. What will happen if the object goes from position 2 to position 1? It's a positive change in gravitational potential energy, my friend, because I'm transferring energy into the object. I'm working against gravity. And if it's the opposite, going from position 1 to position 2, gravitational potential energy is lost. Energy is lost. Okay. So in that case, GPE is negative. Change in GPE is negative. So always better to write this down. Are we clear on that? So always better to do this. Always. This just makes sure that your sign doesn't get changed. All right. So I mean, you could also do another thing. What you could do is, let's say, you always consider R1 to be the smaller distance. So over here, you could just consider R1 to be R2 and R2 to be R1. So you always consider the first part, the first separation to be small, and the next one to be big. And once you get the answer, whatever the answer is, based on the question, if it's going from a larger, farther distance to a closer distance, then you put a negative sign in front of the answer. And if it's going from a closer distance to a farther further distance that is being pushed away, right? Then you say my answer is positive. That's one thing I did, but I was used to it and quick with it, so I didn't sit down getting confused. Okay, wait, which one is my R1, which one is my R2? That's something you can do. You can just consider R1 to always be the smaller separation, R2 to be the largest separation. Okay, benefit of doing that, after getting the answer based on the question, if the separation is increasing, then I say, okay, my answer is positive. If my separation is decreasing, my answer is probably negative. So it's a quick way to do the maths without writing this entire big thing down. But towards the beginning, I'll advise doing this. But this is a big part of your maths. And this is the formula for gravitational potential. Whenever the discussion is with respect to 1 kg of mass, this is the formula. Okay, it's the same thing. It's just 1 kg of mass. And over here, we're talking about any mass. Okay, that's pretty much it. Last thing, even though not extensively in your syllabus, to a good extent it is, not properly, astrodynamics, and that is we want to talk about escape velocity. Can planets really ever escape, let's say, the gravitational force of sun? Can that really happen? Can I increase Earth's velocity for it to escape the orbit around sun, the gravitational pull of sun? Conversations like that, we start talking about astrodynamics. Okay, so what is that? Can I let's first find out the kinetic energy of our satellite. What is kinetic energy? Kinetic energy is simply the energy due to its velocity. Okay, so basically, if my velocity is known to me, I can find out using half mv squared what the ke of my satellite is. Fair enough. Now, do we remember this formula? Probably not. But basically, this is the mv square by r formula. So mv square by r is equal to gmm by r square. So r gets cancelled, m gets cancelled. V square is gm by r. Clear? This is the formula we are working with. So this is how you find the velocity or the orbital velocity of satellite, if you remember from last class. So this is how it's done. Now, how do you find out the kinetic energy? You know the v square value, which is gm by r of the satellite. And I can say ke is half m v square. And what is v square? Gm by r. So the ke, kinetic energy, is what? Half gm m by r. Doesn't that seem so similar? Why does it seem so similar? Half gmm by r. What is potential energy, my friend? What is the gravitational potential energy? Gm negative. Gmm by r. Isn't it? So my kinetic energy, by the beauty of nature, is simply the half of the gravitational potential energy. Isn't that amazing? So if there's something, if Earth is an orbit of Sun, the kinetic energy of Earth is simply the half of the gravitational potential energy at that point of Sun. That's amazing. So even for satellite, if it has minus gmm by r wherever it is near the Earth's surface or away from the Earth's surface, if this is the gravitational potential energy of the satellite, this is the kinetic energy of the satellite just for being in orbit, in orbital velocity. So now compare this. One is half of the other. And that is the very interesting part. So, what is the total energy of my object or the satellite, let's say? The total energy is kinetic energy plus potential energy. So, the potential energy is minus gmm by r. Kinetic energy is positive half gmm by r. Great. And if that is the case, If that is the case, then if I add the kinetic energy with the gravitational potential energy, the total energy of satellite is minus gmm by 2r, or ET is minus half gmm by r. Does this have enough energy to escape? Does this have enough energy to escape? No, because the total energy of the satellite is negative. So if I plot the graph of kinetic energy of the satellite, so basically Ke is given by half gmm by r. So basically, since it's positive, near the Earth's surface, the radius of Earth, it is going to be positive, right? Near the Earth's surface, it's positive. And as I increase the separation, it decreases. Why? Inverse law. Ke is proportional to 1 by r. So if you plot using Desmos online, you'll see this is the graph you get. And again, for the sorry, this is the potential energy. The potential energy, my friend, is what? Minus gmm by r. So it is the exact thing in the negative side. In the negative side. But it is also twice the kinetic energy. There's no half in front of. So if I write it down, gm m by r. While there's a half in front of kinetic energy, there's no half in front of potential energy. So it is twice the magnitude of kinetic energy, but in the negative side. So notice how this thing is displaced in the negative side. Okay, this is a potential energy. Now, what would be the ideal potential energy for the object to escape, for the satellite to escape? The yellow one. If my gravitational potential energy was negative half of gmm by r, yes, then the total energy on the object would be zero. And that means the object is at infinity. Zero energy. What did we discuss today towards the beginning? If the object is at infinity, zero energy on the object. That means the object is free. So if the total energy somehow you can make it out to be zero, then the object will be free. So if you today go out into space and provide the Earth with enough kinetic energy, specifically half gmm by r, the Earth will be vanished out of the solar system. It will go off. It will go off. It will escape the sun's orbit. It will go out, find somewhere peaceful, and remain there. In theory, technically, it's not really possible. But anyways, in theory, if Earth has more than zero total energy, then the Earth can escape the sun's orbit. It can. That's possible if I provided enough kinetic energy. Okay. So how to escape Earth's gravity? The K needs to equal to GPE. So my change in change in kinetic energy, which is half mv square, should equal to the change in gravitational potential energy. What this essentially means is basically I'm trying to find out what the ideal velocity should be. What my ideal velocity should be. So I'm basically equating half mv square, right? Basically half mv square, the kinetic energy that my Earth needs to escape, and that energy must equal to gm m by r. Okay, so this is just a formal way of writing it out. That is to say that the gain in kinetic energy of my Earth should be equal to the loss in potential energy of Earth. So if my potential energy of Earth is minus gmm by r, if the potential energy can reach to zero, then that means that energy is being provided by the kinetic energy. So basically what's happening is the change in kinetic energy balances out the change in potential energy. So if I can somehow make this change of gravitational potential energy from negative gmm by r to 0, then the object is free. And that exact amount of energy should be provided by the kinetic energy. Okay? Okay? So basically, taking the object from wherever it is near the earth to 0, that is infinity, that amount of energy needs to be provided by what? The kinetic energy. The change in kinetic energy. Okay? The change in kinetic energy. Right? So this is the formal way of writing out the equation. But simply, in crude terms, my kinetic energy should equal the gravitational potential energy, as you saw in the graph. If my potential energy is exactly equal to kinetic energy, great, we can escape. So if I just draw it out over here, if this is my KE, that is, I have increased my KE to equal the red side, the red line, then yes, my object will escape. So my KE should be equal to the gravitational potential energy. That is the logic over here. So if you get confused by how it's written, no worries. Don't worry about it. This is the formal way of writing it down. Okay. So basically, the change in KE is expressing that it is going from R1, any given point near the Earth, to infinity. Okay. Okay. And this change in GPE is going back to infinity to get a value of 0. Okay. Fair enough. So what is this velocity that we need? If you understand that my half mv square or kinetic energy must equal to the GPE, then what is the V that I need? Let's make V the subject to understand that. The V should be half mv square is gmm by r. Hence, if I take the m to be cancelled off, then I'm left with V square is 2gm by r. So if I take the root over here, what happens? V is equals to root over 2gm by r. This is called escape velocity. If the Earth has this velocity, which is 2gm by r, you know what will happen? Earth escapes. Earth escapes from the sun's orbit, or the satellite escapes from the Earth's orbit. And that happens all the time. Happens all the time in case of, normal orbits of satellite, let's say. Now, I mean, happens all the time as in we can do that in terms of the satellite. Now, I can't just push Earth to be out of orbit of sun, but like in terms of satellite, sure, you could really do that. Not really difficult. I can just increase the kinetic energy, right? So now, notice this, that in case of Earth, the orbital speed is always smaller than the escape velocity. Hence, we never escape. By how much small? Half gmm by r. This is the kinetic energy of Earth. Now, how will it escape? It can't. Logically, naturally, it can't. Okay. So what is the minimum kinetic energy to escape? I found out the minimum velocity. So what is the minimum kinetic energy to escape? It is simply K is given by half mv square. Did we find out the v square value? Yes. Can I just sub in? Yes. So again, the value comes out to be gm by r, as discussed above. If the kinetic energy is exactly equal to the gravitational potential energy, it will escape. So my ET, total energy, must be gmm by r minus gmm by r. This is the Ke, and this is the GPE. If both are equal, my ET is 0. The object can escape. Are we clear on this? And that ends the entire gravitational fields topic. Okay? Okay? And this is very important. One of the most important chapters you guys have. A few things to note: understand the graph, the force graph, the gravitational potential energy graph. Next thing, understand how to work with the formulas. Understand how to work with the formulas, all the four formulas. Understand how to work with change in gravitational potential energy. Understand geostationary orbits, astrodynamics comes and goes. So just understand the concept over here for astrodynamics today that I just discussed. Okay, and practice questions where circular motion, gravitational potential energy, gravitational force question comes together. Common question. You'll find some such questions. Okay, so practice those. Those will be very important. And then someone asks, yes, gravitational, why is gravitational potential energy negative? Common question, very common question. And I told you guys all the possible answers to it. Okay, so this is pretty much it. Anyone has any question for today's class? We have ended today's class early. I'm done with the topic. There's no other syllabus content left in your syllabus. Anyone else has any question? Are we good with the syllabus right now? Yeah. Okay, I'll take that as a yes. So I'm done with today's class. You're welcome to leave. Hope to see you guys next Thursday, which will be another class. This will be a buffer class. And we'll be starting off with temperature. Okay, fair enough. If we are if you have anything to say, you can. Otherwise, I'll end today's class. Okay. All right. See you lot next class. Bye bye. Good luck.